Hi, and welcome to Chapter 2. This is Section 2.1. Your book is talking about molecular representations in this chapter, or in this section. In this chapter, we're going to talk a lot more about how to communicate about organic chemistry. Because so far, we have really just reviewed general chemistry and kind of left all of the general chemistry things stewing around in our brains, and we still haven't gotten to what is, how do we start talking about these organic molecules? Because in general chemistry, we really only talked about molecules kind of in a sense of the molecular formula, right? We didn't draw very much, and if we did, they were simply in Lewis structures like you see here on the left. So let's go into our notebook here. Okay, so when we communicate organic chemistry, we are trying to learn a language that people all over the world can use to talk to each other simply through writing things whoop, like CH4. If you draw this molecule CH4, everyone in the world who knows anything about organic chemistry can tell you that is methane. They might say the word methane in their language, but they will understand the concept of what it is you're trying to say. And that's what we're going to talk about a lot in this chapter, is understanding the concepts of communication that we use to talk about chemicals. Because you've seen, as we draw Lewis structures, how difficult it can be to start to convey very complex structures. If you have to draw each time the valence structure of carbon, and then you draw the hydrogens, but each carbon is bound to another carbon, and they have hydrogens with their own electrons. You can see it gets very tedious, and it's not an effective way of communication. If you had to talk to someone in a conversation and making simple words took that long, it would really hinder how well the conversation flowed. And in fact, you wouldn't be able to cover much ground, much less be able to even get across very complex ideas. So in organic chemistry, we try and simplify what structures look like in order to be able to convey some of the more complex ideas about molecules. They have drawbacks because in trying to simplify a structure, you lose some information. And so you and the person who is looking at a structure you've drawn both have to have the understanding of what information is missing. But they do allow for communication of more important properties of molecules. So with that backdrop in mind, I would like to show you something here. Because I just said how you lose information sometimes, right? If I were to draw this molecule, if I were to draw ethanol, the thing that makes weekends sometimes really interesting for some people. If I were to draw the molecular formula for ethanol, it would be C2H6O, right? That is ethanol. But this doesn't tell you any structural features of ethanol. With this molecular formula, while it's true in the fact that that is how many carbons, hydrogens, and oxygens are present, methanol, as drawn here, can have this structure, which is the one that we are familiar with, or at least the ones that people typically drink. But this same molecular formula can correspond to this molecule here. They're both C2H6O. One people interact with very often, and one people never do. But the molecular formula doesn't tell you which one you're talking about. So that's clearly not the best way to communicate about molecules. And in fact, often it can be downright misleading. So what's a better way? Well, you just saw me draw a Lewis structure, right? A Lewis structure gives you all of the information, right? You see a Lewis structure and you can know which carbon is bound to which other carbon, which hydrogen is bound to which carbon. You can see all the bonds and all the lone pairs there. But the downside is that it takes a long time to draw. As I said before, it's not so nice to have to draw Lewis structures everywhere. So scientists started to go with scientists started to figure out different ways to communicate molecules, such as we know that we're dealing with this structure here, right? What if we communicated each individual part of the structure, such as H3C? That is a carbon with 3 hydrogens. That's there, right? And then to that, next we can put CH2, because this section is CH2, and then OH. Or I should do that in a different color just to really do that. There we are. And that's that section. This is called a condensed structural formula, and it does allow for a little bit more like of a truthful molecular formula to be able to communicate with others. However, it gets a little complicated if the molecular structure gets complicated. For instance, I can draw this molecule here, and I'll draw it in the Lewis structure first, and drawing it in the Lewis structure can tell you just how long it takes to really draw complex structures. It takes a while. And I'm not even drawing them exactly correct, remember? Because we have to put in all the dots. So if we were to draw this molecule, all carbons and hydrogens, its molecular formula is C12345 H 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So it's C6H14. That doesn't tell you much. There are many, many types of C6H14 molecules, right? That was even one of the problems in the back of the book in chapter 1. But if we drew it as this condensed structure here, then we start to break it up into pieces. And there we could say we have H3C as before, but then it gets really complicated with this section, because now we have C here, and that carbon has 2 CH3 groups attached to it. But then we can get back on track and we can say CH2 from this one, and then CH3 from this one. So you can see that you can communicate a little easier there, but it does maybe make things complicated as you start to have these more complex functional groups or complex substituents onto a carbon. And substituent is a word that we use in organic chemistry, which means something bound to something else. So for instance, the underlined blue carbon here, it has 4 substituents, 4 things bound to it. It has 1 CH3, it has 2 CH3s there, and the 4th one is that group. I'll draw them in the structure here. 1, 2, 3, Four different things bound to it. Those are substituents. So this is almost a really good way of talking about structures, but we still get kind of confused because of just the nature of reading from left to right these condensed structures here. Instead, what if we use what are called partially condensed structures, where you don't draw out all of the CH3s? That might make it a little easier, and it might be a little faster to draw. So what if instead we'll draw ethanol again. We'll come back down and we'll draw this one again. So now we would say, yeah, exactly. So in the partially condensed structures, how we draw them to communicate is that we only make the bonds between the important atoms. And the important atoms are ones that are not hydrogens. So hydrogens typically get left off. And as you see here, we made the bond between the carbons and the bond between the oxygens. But the H's we just left as H3, H2, and H. We just leave them alone. But this also can lose some information, right? It can lose some information because if the molecules get more complicated, it gets a little ambiguous as to where the H's are and where they go. And it still takes some time to draw the H's in. And it doesn't seem like that should matter very much right now, but molecules get complicated very quickly. And if you're always having to draw the hydrogens in, then again, you're losing a really nice way to communicate chemistry. And you're maybe giving too much information about a structure, because maybe the most important thing isn't the hydrogens. Maybe the most important thing is to think about what actually is the overall structure of the molecule. And that might sound stupid to you at this moment, but I would reason to say that if I were to draw a very complicated molecule, even the partially condensed structure that I just drew isn't enough. So in light of that, chemists decided that really all we need is to know where the carbons are and where the other non-hydrogen atoms are. So using the same example of ethanol, there was another type of structure that was made called bond line structures. So in bond line structures, that's what ethanol looks like. In bond line structures, you only draw the carbons as vertexes. So you draw from one point to the other. It's kind of like how you only draw the bonds. You don't actually draw the atoms. So if you were to draw something like this, just as another example, if you were to draw, I'll draw it in condensed structure first, as I did before. So if you were to draw, actually, let's use this one. Let's use this one here, because we already saw how complicated that one was to make. But if you drew that structure, the one that we have in the totally condensed structure, if you draw it in partially condensed form, you would have H3C, carbon, CH3, CH3, CH2, CH3. And that's pretty informative, but you saw how long that took for me to draw. This is how fast it is to draw bond line structures. There you go, and it's done. So again, in bond line structure form, you never draw the carbon, or you never draw the hydrogens. You only draw bonds between carbons and from carbon to other things. And it saves a lot of time, with the downside that you don't know, or you have to remember that the hydrogens are there. You have to remember also how many bonds that carbon, oxygen, nitrogen etc., like to make in bond line structures because they aren't shown. So in this structure, you have to remember that there are 3 hydrogens attached to that carbon, that there are 0 hydrogens attached to that one. Both of these have 3 hydrogens. This one has 2 hydrogens, and this one has 3 hydrogens. This information is intrinsic, meaning that the representation dictates that the information is there, but it is something that is not shown to you. You have to remember that it is present. So we'll talk a lot more about molecular representation in bond line structures, but what you need to know is that um, that the representation you choose for a molecule and the one that's shown to you all have their own drawbacks, and they all have their own positive points too. And it is in remembering what each structure gives and takes that you can really effectively communicate about chemistry, organic chemistry specifically. So this has been an introduction to chapter 2 and chapter 2.1.